Okay, so let's get started. Lecture 13. Looks like Friday is a bad day for a lot of people. I know there are some people who are doing some TA work also. Let me get this other screen up. Okay, so as usual, we'll start with a review. We're doing the method of stages, and we applied the series stage, this thing in circle here, to the MER system. So every customer that comes in has to go through R stages of service. That gives us a service time density, which looks like this. It's a whole new family. This is the state diagram from which we could write down the equations, form the P of Z, solve it, and this was the answer for MER1. I just remind you of that because we're going to use some of that in just a moment. ERM1 we also did. In that case, the inter-arrival time density is the Erlangian. The service time is a single exponential. Here's the state diagram. Off we went. We found P of Z. We recognize how nice it is to end up with getting P of K. You only need one constant, this Z0. And we're done. So now we've started to do bulk arrival. And I made the point that in the bulk arrival system, it's a pure MM1 system, but our customers come in with each arrival. And the state diagram we drew, and we said, look, that looks like, I'm going back up now, that looks like this MER1 system. Because every time in MER1, when somebody comes in, they bring in R stages. In the bulk arrival, every time someone comes in, they bring in a total of R customers instead of one. And I made the point that the MER1 system solves the bulk arrival system when the bulks are all of the same size. And some people had trouble understanding how this queuing picture with stages maps into the bulk arrival. I mean, what happened to all these stages? And the answer is, the physics is hard to understand, but if you look at the state diagram for this and the state diagram for the bulk arrivals, just changing R mu to mu gives exactly the same picture. Again, an arrival brings in R. At each stage, you're dropping down by 1 at a rate mu instead of R mu. So this is exactly the same picture. Therefore, the P of Z must be the same. It's a little hard to interpret the fact that there's no stages here. It's a single service. But if the state diagram is the same, then you can't argue that the result won't be the same. And it is. So let me come here now. What's going on here? Sorry. I'm having, it's giving me a little trouble here. Bear with me a second, I'm sorry. Okay. So we solved the fixed bulk size from MER1. But now, as I said, we're going to be more generous. We're going to allow a random number, a random bulk size each time an arrival comes in. GI is probably the bulk size is I, not always a fixed number R. And in that case, we saw last time that the state diagram looks like this. I showed you only state K, and for state K, we notice when an arrival comes in, with probability G1, you add one more, so you go from here to here. With probability G2, you go up 2, etc. So these are all the ways out. And there are many ways in from below. In fact, you can enter state K from any state below. An arrival comes in, if there is a bulk size, that'll take you from any state I into K, if it's GI, in fact. This is coming in from state I. And we want to find, again, always the probability there are K in the system. Now, I made the point, and I'll make it again, that if you try to basically balance around the state K, we're going to get the following kind of system. First of all, what is the rate of leaving state K? Well, certainly mu plus some arrivals out of that state. So let's see, there's a lambda G1 if the bulk size is 1, or at a rate lambda with probability G2, it's size 2 on up, which is simply mu plus lambda times the summation of all the possible G's. And what is that sum? How big is that sum? Exactly 1. So that's equal to mu plus lambda, which is very handy. And now let's continue. Let's look for, just 1 second. So now by inspection, let's do the full circle around this red state. So the rate out, we just said, is lambda plus mu times what probability? P sub k. That's the rate of probability flowing out of the state. Let's look at the rate flowing in. Certainly, it's going to be mu p k plus 1 from above, plus you can enter from all the states below. So it's going to be a sum of all states I equals 0 to any state below, namely up to k minus 1, of probability in that state I times basically G sub what? For a given I, how many have to arrive to drop you into state K? You had I, you need K, so you need K minus I coming in. Whoops, K minus I. So that's the balance equation, and that's good for K greater than or equal to 1. Now let's do the lambda 0 case, the P0 case. Clearly we're going to have simply that the arrival rate out of state 0 equals the rate into state 0. You can't come in from below, you can only come in from above, and that's at a rate mu 1. So that's a K equals 0 case. And we also need the summation of the probabilities going to 1. Okay, let's use Z transforms on that equation. So we're going to multiply Z to the K, sum over all K, and the K ranges from 1 to infinity. So let's do that. We're going to get lambda plus mu times summation P K Z to the K from K equals 1 to infinity. On the right-hand side, we got a pk plus 1. We already know we're going to have to add a z and get rid of a z. So I'm going to take mu, get rid of the z I'm going to add, and now sum from k equals 1 to infinity of pk plus 1, z to the k plus 1. And then we got another one. Now we got this funny term. It's going to be the equation at the top of the page is wrong. I left out an item. What did I leave out? What's that? Lambda, of course. So we're going to pull that out now. We're going to get a sum from k equals 1 to infinity. And again, why am I going from 1 to infinity instead of 0 to infinity? Because the equation I wrote down is only good from 1 to infinity. Remember, sum over the appropriate range. This is a special case. It doesn't satisfy the equation above. So that's why I'm stuck from 1 to infinity. And then I've got this other sum, I equals 0 to k minus 1, of pi g k minus I times z to the k. Well, son of a gun, I got a double sum. Now I'm going to pull a usual trick on you. Let's write down that double sum all by itself. And I want to exchange the order of summation. That's what I'm going to set up to do, because it leads to a very nice result. So summation k equals 1 to infinity, summation I equals 0 to k minus 1. And I want to plot that on the ik plane. And I've already prepared the picture, so I don't have to draw it too carefully. So I'm just going to copy it, because it wants to be drawn fairly carefully. So let's put that right here. So what you see here, excuse me, is the I is the vertical axis, and A is the horizontal axis. Now let's look at what this expression here, which I'm going to turn to the color blue on. Let me I see the trouble. Okay. I want to change this to blue. Actually, I should have done that to red. I'm sorry. Let's look at k equals 1 to infinity. I goes from 0 to k minus 1. So choose a k. Say you choose k equal to 4. If you choose k equal to 4, then I goes where? From 0 to 3. So it means I'm going up this column I painted in red here. I goes from 0, 1, 2, 3. And by the way, to make life a little cleaner for all of us, I should put this properly on the graph paper. That's a little better. So by running k from 1 to infinity, I'm going to cover all those red dots. I'm covering an infinite triangle. On the other hand, and I'm going to write this in blue now, I can write this as follows. I also claim this is equal to sum from I. Well, where does I go from? It goes from 0 to infinity. You can see that there's an axis. Now summation k goes from where? You'll see it's equal to I plus 1 up to infinity. And let's check that. I should write that in blue. Let me change the color. If I look at this sum, choose an I, say I equal to 3. What does k go to? From 4 to infinity. So k goes from 4 on up, namely, it's this blue rectangle. And now I'm going to let I change from 0 to infinity, so the blue is going to move up and down and cover all the red dots again. So this is an equivalent change of order of summation. And if you're ever confused about it, draw a picture like this, and you'll see that it'll be correct. Anybody have any question about why I've gone from red to blue to change the order of summation, and the range is correct? Again, either you're running a bunch of red Either you're running a bunch of these red vertical blocks. Here's another one, and it goes all the way out. You're going to capture all of this. Or you run in these blue rectangles. There's one, here's another, and you're covering the same space. You just have to be careful as you're on the indices, and we've been careful here. Okay, now once I get that, if I look at this interesting term here, this double sum, which is in my balance equation down into the z transform, I can write that as follows. So that summation, which I had, I'm going to rewrite it, k equals 1 to infinity, summation I goes from 0 to k minus 1 of, put the lambda in front of it, let's not forget that again, pi gk minus I z to the k. Now let's change the order of summation. We got the lambda. First I want the summation I equals 0 to infinity. And when I look at the expression top of the page, pi is independent of k, so I can pull that out under this sum. And I know I'm looking for z to the I, so let me put it in and I'll take it back and I'll give it back in a minute. And what's left, let me just move this over a little bit. What's left is this other sum, k equals I plus 1 to infinity of g sub k minus I. Now I had a z to the k. I took away I. I got to have to give it back, so I got z to the k minus I. How convenient. It's exactly the right order. And if it was inconvenient, I'd pull something out in front here and make sure it was the right number, but it happens to be good this time. Okay. Well, let's look at these things. First of all, what is this thing? Yes, it's P of z, of course. I didn't write it out for you explicitly, but that's what I'm cooking up when I go to the z transform. And what, pray tell, is that? First of all, when k is I plus 1, okay, it goes from g sub 1 on up. So that's a summation of g sub k z to the k from 1 to infinity. What do we call that? It's a z transform of this distribution. Namely, I'm identifying that this is g sub I z to the I. That's by definition. And a P of z, of course, as always, summation P sub k z to the k from 0 to infinity. Now, you might wonder, this 1 down here is a little bit, why didn't I choose 0? What is G0? Well, I could include it, but it has a value 0. So I don't need to include, I can put it in for free. We could have included it. So we're doing fine. So suddenly, this nasty term up here is suddenly a very simple term. It's lambda times that product. So let's write it out now. So I've got that going back. I've got lambda plus mu going up to this equation here we started forming it. What is this sum up here? What is that? It's P of z missing the 0th term. Remember, there's a 0 down here. So I'm going to put it and take it away, okay, as usual. So that's P of z minus P0 z to the 0, which is 1, so just P0. That's little P0, I'm sorry. On the right-hand side, I've simply got, well, let's see. When k is 1, I start at 2. Oops. If I call that p of z, I got to put back 0 and 1. Okay? So that's mu over z. And I get p of z minus the first two terms. I keep writing this capital P, I mean little p. This will be a p of z minus a p0 minus p1 z to the 1. Plus what I just cooked up, which is lambda p of z g of z. But let's not forget that there's a zero equation. The zero equation up here told me, it's right up here, lambda p0 is mu p1. Well, let's see. There's a lambda p0 right there with a negative sign. And there's a mu p1 right there with a negative sign. So they cancel. So I cancel this, and I cancel this one piece here. Okay? And I'm going to factor out p of z while I'm at it and solve for it. So p of z equals the following. What's left upstairs which is not p of z? Well, there's a mu p0 on the left-hand side, so on the right-hand side it becomes mu p0. And I also got a mu over z p0. Everything else is in the denominator. I got a lambda plus mu p of z. I've got a minus mu over z. And I've got a minus lambda g of z. Okay. Now let's do a little bit of factoring. What wants to be factored here? Clearly, 1 minus z is all over the place. So let's multiply. Let's multiply everything by minus z, and I'll get the following. I get a mu p0 times a 1 minus z, and I multiply by a minus z, and I'm going to get this lambda plus mu will come in the middle here, minus lambda plus mu times z. And the mu over z becomes just plus mu, and the minus lambda g of z becomes plus lambda z g of z. I just multiply by minus z. And let's do the factoring now. Let me write this down again. Upstairs is mu p0, 1 minus z. And downstairs I see it's mu times 1 minus z minus lambda z, 1 minus g of z. Now, of course, we expect z equals 1 to be a root of the denominator always. And it's going to cancel the one upstairs. We'll get to that in a moment. It's not obvious yet what to do with it. But I want to get rid of p0. How can I get rid of p0 now? What haven't I used yet? One more equation that I always need. That's right. Sum of the probabilities is 1. So let's use p of 1 equals 1. But oops, that's 0 over 0. L'Hopital is going to help us, okay? That's going to be equal to the limit as z goes to 1 of L'Hopital's. L'Hopital's is going to give me, upstairs I get a minus mu p0, and downstairs I get a minus mu, and then I'm going to get two terms here. I'll get a minus lambda 1 minus g of z And also I'm going to I'm going to differentiate this thing. I'm going to get a lambda z g prime of z. Now when z goes to 1, it's okay. So that's going to become minus mu p0 over minus mu. Now what happens to this 1 minus g of z when z is 1? G of 1 is 1 also. So that middle term goes away, and I get just a plus lambda g prime of z. Oh, g prime of 1, I'm sorry. Okay. If that's equal to 1, that tells me that I'm going to get the average number, etc. Basically, we're going to get that rho. Let's define rho. Rho is going to be equal to the arrival rate times the average number that come in per arrival, which is g prime. That's the average bulk size, over mu. We're going to define it that way. So P0 from this expression above is simply 1 minus rho, as always, where rho is defined above. Okay, so let's finally write out P of z. It's mu 1 minus rho. I just put in, whoops. I just put in for P0. I'm still stuck with the 1 minus z upstairs. Remember, I'm plugging in to this equation at the bottom of that top page. And downstairs, I'm going to get a mu 1 minus z minus lambda z 1 minus g of z. Okay, that's basically the answer. Once you give me the distribution of bulk size, I can calculate g of z, and I'm done. And of course, there'll be a root of z equals 1 in the denominator, of course. Now from this, we can easily find the average number in system, namely summation kpk. And if you do it, you're going to get the following expression. You're going to get rho over 1 minus rho, just to give you the answer now, times the second moment of g minus the first moment of g, which you can get from the g distribution, over twice g bar. And the variance of the number in system will equal, again, rho over 1 minus rho times the following expression. I'm not doing this, I'm just giving you the answer here. It'll be 2g cubed, third moment, minus 3 times the second moment, plus the first moment. All of that over 6 times the first moment, plus the mean number squared. Now, just for fun, if the bulk size is 1, namely g sub I equals 1 for I equals 1 and 0 otherwise, namely fixed size bulk 1, that's the old MM1 system, isn't it? Okay? If we chose instead arbitrary fixed bulk size, fixed bulk size of R, namely G sub I equals, with probability 1, the size is R, and 0 otherwise, then what do I have? I have a solution at the top of the review today. It's the same as M E sub R1 with R mu replaced by mu, as I said before. Insist on doing that, okay. So we've done it. And if you look at that, what will G of Z be in this case? It's simply Z to the R, right? G of Z is summation GK, Z to the K, or I, it only takes on the value R. And that gives you up here, G of Z is 1 minus Z to the R, and that's what we had before. So it's all consistent, and we're done. So essentially what we've done here is we solved an arbitrary bulk size MM1 system. We solved bulk size. By the way, there's a whole set of queuing literature for dealing with other queuing systems besides MM1 for bulk arrivals. This was the simple one, MM. You can do MG as well. And that's a whole sophisticated study. Okay. Now, what do you think is the next thing I'm going to do? What's the next natural step? Well, let's go back to our review today. I just took MER and I recognize it's a bulk arrival. ER1, which looks like every time a customer leaves, he throws away R stages of arrival in ERM1. That's like every time a customer leaves, R people leave. If this was not stages, if it was customers. So this looks like a bulk service. So that's what I'm going to do next. That's the answer to my question. What do you think I'm going to do? Well, I know what I'm going to do. It's bulk service, okay? So let's look at a bulk service system. Because we already solved one from ERM1. And that's basically the same as MM1, and I'm going to call it bulk services. I'm going to let you know it is MM. Well, I've already suggested that basically ERM1 looks like this because every time something leaves, it takes away R things. That's like R people got service at the same time. Okay? So let's choose exponential service at a rate mu, of course, arrivals at a rate lambda, but every time somebody leaves, they take away R. So every time somebody goes into service, no R people go into service, and they all get served as if they were one customer at a rate mu. So if I was a servant and somebody just left, I'll take 5 of you guys, you all come in together, you get served as if you were one. But there's a question. What happens if there's not R of you? What happens if there's only 3 of you instead of 5 of you? I'll take in the 3. But now there's a question. Well, I'm serving the 3. And by the way, when I take in the 3, the system is empty except those in service. There's nobody in queue. What if somebody arrives now? Should I take him in or not? And you consider both cases. I'm going to assume we take them in until we get R. It's a free ride. The 3 that I took, I start serving exponentially. I bring in a 4th. It's exponential, remember? So I don't care how much service I've given. It's as if we started over again. So I keep filling up until I get R, and if I don't get R by the time I'm done, as few as I have leave. So it's a rather interesting system. So let's try to say that, okay? R taken into service as soon as the last bulk leaves. If less than R in the queue, say a number K less than R, taken K. But while these K are being served, any new arrivals can join service until we get R. If service ends with less than R in service, empty the smaller bulk and continue. Now, suppose that happens. I had either a full bulk of size R, suppose I had less than R in service, and I'm finished. The service ends exponentially. When that bulk leaves, tell me what the system looks like. Empty. Because if it was not empty, more people would have joined me in service. So for sure it's empty. And now the server waits around for the first guy to come in, and what happens? Yank, he grabs the one guy. Starts serving him. If another one comes in, he grabs him again until he gets up to R or less than R and goes out. So I'm making you think this way because that's the physics of the problem. And notice we had some choices. And if you're going to try to model a system and analyze it, you have to be explicit about these choices. You have to make sure you got a machine that covers a protocol that takes all the cases. And we chose a particular form of that case. Okay, so this is the one I'm going to choose. Okay? So let's draw the state diagram. Now, it doesn't quite, if I go back to ERM1, it doesn't quite look like this, does it? What's the difference? What do I have? It's going to look similar to this because this shows R leaving whenever there were R in service. But what would be different in the state diagram I'm going to draw right now? Yes, you'll be able to leave even from state 1. Service finished, one guy leaves. If you had 2 in service, 2 will leave. So there are these terms that I have to add to my state diagram. So let's draw that state diagram now. This is a large state diagram. Okay, I didn't fit it all. I'm going to force myself to fit it all in. Okay, let's draw some circles around these. There's a lot of dots around here. Let me put them in. Okay. So, if I'm in state 0, what can happen? It's an MM system. One guy can come in. At what rate? Lambda. Okay. If I'm in state 1, I can have an arrival. So out of every state, I can have an arrival. Let's draw those in. These are all lambdas. Okay, so now departures are different. Suppose I have K in the system. I can arrive to it from state below it, from K minus 1, and a new arrival will push me to state K plus 1. But if I get a departure, where does it go? K minus R, exactly, because the way I've drawn this, K is bigger than R, so I know there was at least R in the system. So all R are in service. So we're going to get a departure at what rate? Mu. Similarly, from K plus R, I'll come down here, etc. Now from R, let's look at state R. Where do I go if there's a departure? 0. Where do I go from state 2 if there's a departure? 0. From state 1 if there's a departure? 0, etc. But from R plus 1, I go to 1. And all of those are at mu, etc. That's the picture. Again, you got to get this right because you're going to balance these equations. Okay. So now let's define once again what we want. We want pk is the probability of k in the system in equilibrium. And by system, again, I always mean Q plus surface. Okay? Okay, let's look at k greater than or equal to 1. You notice as I look at all of these states that I've drawn complete, like state k, let me add a couple of more items here. Every state has 4 arrows except state 0. From any state, I can go down by a departure. I can enter from above by a bulk departure, or by an arrival from below, and I can have an arrival taking me out of that state. So they all look the same except state 0. How convenient. So let's write that down. Clearly, the way out is just lambda plus mu, an arrival or a departure. I have an arrival. I go up by 1. So this is the way out, okay? And all of that times what I had, pk. Now, how do I come in? I can come in from directly above, excuse me, by r above, mu p sub k plus r, or with an arrival from the state below, lambda p k minus 1. And for k equals 0, it's a little bit interesting. I can get out of there with an arrival, so lambda p0 is the way out, and the way in is where? With an arrival from any one of our states. What are those states? It's state 1, state 2, up to state R. Okay, the physics is done. The thinking is done. Now the mathematics comes in. There's a set of linear difference equations. I need to solve them to find the pKs. Usual approach, Z transforms. Suddenly, once I go there, my mind is gone in terms of what's happening in the system. I'm only playing with mathematics. And understand, that's what happens to you when you do these procedures. At the very end of the course, I'm going to show you how to keep the physics going longer into the analysis. But right now, we're basically subject to becoming mathematicians and no longer physicists. So let's define P of Z, as always, summation pk z to the k over all k, 0 to infinity. And let's multiply the basic equation by z to the k and sum on all k. So I got lambda plus mu times the summation. The range is from 1 to infinity of pk z to the k equals, and I'm going to sum again. And I know, since I got pk plus r, I'm going to need a z to the k plus r. I'm going to have z to the k, so add it and subtract it. So I'm going to take mu and z to the r downstairs, and upstairs I'm going to basically get summation p k plus r, z to the k plus r, and k goes from 1 to infinity. And then the next term is this last term. I can put that right here, lambda summation. Well, I need an extra z, so let me take it out right now. Let me take out a z, so I'll get a sum from 1 to infinity, basically pk minus 1, z to the k minus 1. Okay, so let's form what we need. The usual trick, look for P of Z. It's all over the place. So I got lambda plus mu. It's almost all there, but I'm missing the 0th term. So that is P of Z minus the 0th term, which is simply P0, equals mu over Z to the R. Now when k is 1, I start off with r plus 1. So let's put them all back and give them back. Put them all in and take them back out. And that'll be all of P of Z minus a sum, which I didn't have. And that sum is a summation k equals r, 0 up to r of pk z to the k plus lambda z, and it's all there when k equals 1. I start at 0, so I get P of Z. We've done this so many times, it should be easy, and you should be able to do it correctly on an exam. Okay, instead of collecting all this, now let's take the break, and we'll do the rest of the algebra when we get back. Okay, let's continue. So let's simply factor out P of z in this equation and get the following expression. So what's upstairs? Well, we get this lambda plus mu times P0. And I'm going to multiply, this equation is just asking for me to multiply by z to the r, so I will. So I'm going to be left with lambda plus mu P0 z to the r on the right-hand side. And it's a minus sign since it's going to the right-hand side. Minus lambda plus mu P0 times the z to the r I multiplied by. And the other term I get is that funny sum. And that sum is a plus mu summation k equals 0 to r pk z to the k. And I multiplied by z to the r to get rid of this. Okay. And then I get p of z's, and those are just downstairs. I'm getting lambda z to the r plus 1. This lambda times p of z gives me lambda z to the r plus 1. That came from this term over here. I multiply by minus 1, that's why it's a plus sign. Minus lambda plus mu, all of that times z to the r multiplied by it. And all I have is plus mu left over from this other term here. Okay. Now, let's look at the k equals 0 equation, which I'm going to need now. That's this equation right here. Let's write that out. That says that lambda, lambda, and I'm going to put this in a paren, leave it open for a moment. You'll see what I'm going to do. P0 says lambda P0 is equal to mu times the sum from 1 to r. Of little pk. Now, if I, in red, add mu on the left-hand side, I've added a mu p0 to the left-hand side. If I change this lower limit to 0, I've added mu p0 to the right-hand side. So that's legal. And I'm also, let's do another color, I'm going to multiply everything by z to the minus r. And now look what's going here. I've got this funny term here, which is equal to a sum. So I'm going to take advantage of that and finally write the equation as follows. That P of z is equal to summation k equals 0 to r minus 1 of pk times the difference z to the k minus z to the r. So I'll multiply through by z to the r. And downstairs I get r rho z to the r plus 1 So I've multiplied basically, but change that lambda to a rho, as you'll see in a moment, minus 1 plus r rho, all of that is z to the r, plus 1. Namely, I've divided by mu, where rho is equal to what you would expect. It's lambda over mu r. It's mu r because I'm pumping r people out at a time at a rate mu. So that's basically the service rate, looking like that bulk arrival system. And by the way, do you see something a little strange that I've done? Do you notice that this is r minus 1 and not the r that we've been talking about up here? But when this is equal to r, I get z to the r minus z to the r, so it cancels out. So for free, I can drop that down. Makes it a little bit simpler. Okay. Now this whole thing, we're going to have to do a partial fraction expansion. Let's play our usual game. Let's write this as a numerator in z over a denominator in z. Now look at that denominator. You probably don't recognize it, but if I go back to ERM1 in the review today, look at that denominator. It's exactly what I just cooked up. So I know all about its roots. We spent a long time diving in, Boucher's theorem and all the rest last time. Well, we know an awful lot about that now, okay? So let's say this. So d of z is same as for ERM1. So use same arguments to locate roots of z, d of z. And what is the answer? We know the answer. One root is z equals 1. R minus one of them for absolute value of z less than 1, such that absolute value of z less than 1, and 1, which we denote by z0, is such that z0 in absolute value is greater than 1, outside the unit circle, if you will. Now, if you look at the numerator degree, n of z, is degree r. Okay? So let's talk about that. N of z degree is r. And where's one of the roots? By inspection. Give me you see an obvious root of the numerator. It's always there. Z equals 1. Z equals 1, numerator goes to 0, okay? So let's say that. One root at z equals 1. But remember, P of z is bounded in the region absolute value of z less than 1. And remember, there's these nasty guys. And I can't let them sit there because then the denominator would go to 0. The function blows up, not allowed for z less than 1. So basically, the numerator has to match those. R minus 1 roots must match these. That means that these two polynomials of degree r minus 1, what's left over after you take out away z equals 1, must be proportional. Using the same kind of argument we did for ERM1. So what can we say? So here's a proportionality constant. The numerator degree is that summation pk z to the k minus z to the r. Write it down. After you take out the root at 1, so let's do that. Let me write this more carefully. It's a good k. Take away the 1 minus z must be the denominator polynomial, which is all of this. I'm going to actually copy it. Over the two other roots in the denominator, namely, these are the r minus 1 roots. I only want those r minus 1 roots, so I'm going to take away this root and that root. So let's take it away by writing down 1 minus z and 1 minus z over z0. A similar argument to what we used before. So if we cancel the common factors, we'll get the following. P of z is what's left over, namely, the only thing that's left over is the 1 over 1 minus z over z0. And there's a k multiplying the whole thing we have to evaluate yet. And we're going to get k, Matt? You got a few answers. P of 1 equal to 1, okay? So let's do that. Okay. You find that out and you find out what k is. So k will equal 1 over 1 minus 1, 0. K equals 1 over 1 minus 1 over z0. So that gives you this. So P of z, it's a very simple function now. It's equal to 1 minus 1 over z0. That came from the k downstairs. Over the root 1 minus z over z0. And by inspection, I can invert this thing. It's a simple one-pole function. It's that constant 1 minus 1 over z0 times 1 over z0 to the k. And that's good for all k. Son of a gun, geometric again. Not too surprised, since it was very similar to ERM1. So let's draw a box around that. That's the answer to the bulk service case. Now, if you want to check it, why not? Let's check it for MM1. For MM1, we basically need what? Bulk size equal to 1. Bulk service size, okay? Well, we did this before. Z0 turned out to be 1 over rho. And pk turns out to be 1 minus rho to the k, which we know, so it checks out. And how do we find z0, by the way, up here? You find it by forcing the denominator at z0 to equal 0. And that gives the equation, the one we saw earlier. It's r rho z0 minus 1 is equal to 1 minus z0 to the minus r. Okay, so that's the end of that. We're going to move on to something else now. So what we've done with this method of stages, we introduced the idea of the Erlangen distribution. Erlangen takes you from exponential all the way down to a unit impulse. But what's one property of all of those? It's so restricted to a certain range. You remember we showed for the Erlangen that c sub b squared was 1 over r, the coefficient of variation, okay, variance of the mean squared. It's equal to 1 over r, so cb, which is with this coefficient of variation squared, coefficient of variation itself will in this case be 1 over the square root of r, which is always less than 1. So we got things which are less variable than exponential. In fact, when we went to the impulse, that's got 0 variance. And each of those Erlangen distributions gets narrower and narrower relative to the mean. Okay, so it's a restriction. Okay, so let's try to generalize it a little bit. We're going to call this series parallel systems. In other words, Erlangen is not done with us yet. He's going to show us some more. It's a generalization. Well, one way I could generalize that we haven't looked at before was the following. We could can't write very well, I'm sorry. We could study, we did MER, we did ERM, we could study E sub R slash, let's use an R for the arrival, and an E sub RB slash 1, namely different values of number of stages. Okay? But that still gives us CB less than 1. Remember, CB for all of these was equal to 1 over the root of R. It's more regular than Markovian, than the exponential. So let's ask ourselves, let's consider a way, basically, to make it less regular than the exponential. I.e., CB greater than 1. So let's think about this. Let's try to generalize things. For example, one thing we could do, perhaps we could use an R-stage Erlangen where each stage has a different rate. Maybe that'll give it some more variation. So let's consider that, okay? Case 1. Consider an R-stage Erlangen I'm not yet talking about a queuing system. I was just talking about densities. An Erlangen is a density. I could consider an R-stage Erlangen with a different value I'll call it a different rate for each stage, say for the ith stage. I equals 1, 2, up to r. Namely, B star would look like this. It will be, ordinarily, it's mu over s plus mu to the r. But now each one of those is not the same. It's going to be a mu1 over s plus mu1 times a mu2 over s plus mu2 dot, 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 mu r over s plus mu r. In the moment, from the moment generating properties, after I want to find out what the coefficient of variation is, moment generating properties of B star will allow me to calculate them. Namely, as you recall, the nth derivative of B star of S at S equals 0 is, anybody remember what it is in terms of moments? It's on my blackboard. Yes? The nth moment. That's exactly right. You don't want to forget the minus 1 to the n times, I'll use x to the n bar, where x is the surface time. Okay? Where does the minus 1 come from? Remember what B star is. B star of S is equal to the integral from 0 to infinity of B of x e to the minus sx dx. When you differentiate with respect to s, that minus comes down. Namely, you get a minus x, then a plus x squared, and a minus x cubed, etc. That's where it comes from. So that'll help you remember it, perhaps. Okay. If you do that, that's just a little bit of arithmetic. What do we get? We get that the coefficient of variation squared will be equal to the following. The summation of the 1 over mu I squares, namely the second moment squared, the first moment squared, summation 1 over mu sub I squared from 1 to r, over the sum squared, summation of 1 over mu I from 1 to r, that quantity squared. Now, turns out there's a nice inequality, which you don't even need a name for it. You know what it is. Suppose you got a bunch of AIs, which are them greater than or equal to 0, which is true for the mu's. The 1 over mu's are all greater than or equal to 0. Then it's the case that the summation of the AI squares, say over all I, is less than or equal to the sum of the AI's quantity squared. Anybody see why? Let me write it out. Left-hand side is A1 squared plus A2 squared plus dot, 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 plus A sub r squared. I'm saying that's less than or equal to the sum of the AI's, which is A1 plus A2 plus AR times the same thing, A1 plus AR. Now clearly on the right-hand side, you're going to get a sum of the A squared and all the cross terms, and they're all positive. So if you only consider the square terms, the right-hand side becomes smaller. Okay, so that's obvious. Okay? Well, if that's the case, then this baby downstairs is greater than the upstairs. Son of a gun. C sub b squared, again, is less than or equal to 1. Does not do the job that we want. Does not help. So I took you down that garden path just to show you it doesn't work. Okay? So sending customers through a series of exponentials is not doing it. CB squared is still less than 1. So guess what? Look at the title of the section here. How about some parallel stages instead of series stages? Okay. You get two choices, so let's try parallel. Okay. So let's look at parallel stages. Okay. Let's draw it. Let me draw the picture. Suppose I have a service rate at mu1 and another one at a rate mu2. And I let customers come in, and either they decide to go through the upper guy or the lower guy. And no matter which one they chose, they then leave. And this thing in red is the service facility. And let's assume that with probability alpha sub 1, they choose mu1, and with probability alpha 2, they choose mu2. Clearly, alpha 1 plus alpha 2 is going to equal 1. But I'm choosing the alphas general because I'm going to go to more than 2 in just a moment. So this is stage 1. This is stage 2. This whole thing is a service facility. One customer at a time. One customer inside at a time. And of course, in this case, alpha 1 plus alpha 2 equals 1. Okay, if that's the case, would somebody please tell me what the service time density is? Well, with probability alpha 1, it's going to be mu1 e to the minus mu1 x. Or with probability alpha 2, it's going to be mu2 e to the minus mu2x. This is good for x greater than or equal to 0. And therefore, B star of S is equal to, with probability alpha 1, this converts to mu1 over S plus mu1, plus alpha 2, mu2 over S plus mu2. Now you can see where this is going. I'm going to generalize it now to n stages in parallel. Okay? So let's say that. Let's say capital R stages. And if I do that, given that the summation of the alpha i's from 1 to R equals 1, I can immediately write down what B star of S is for this R stage parallel server. It's the sum from I equals 1 to capital R of alpha I mu I over S plus mu I. This has a name. This is called a hyper-exponential. It's more than exponential. Distribution. And the symbol we use for that is capital H sub r. You used E sub r for Langhian, which is hypoexponential, H to r for hyperexponential. The mean service time is what? It's a summation of the alpha-weighted individuals. With probability alpha I, the mean service time is 1 over mu I. This goes I equals 1 to r. The second moment is equal to the summation. And we've done the second moments before, so it's twice for each one of these we're going to get. We know it's twice 1 over mu squared, except now we have to sum them from 1 to r of alpha I over the mu sub I squared. So let's do the coefficient of variation to prove it's bigger than 1. That's equal to the variance over the mean squared. And here we have, what is the variance? Second moment minus the first moment squared. So that's x squared bar minus x bar squared over x bar squared. That's equal to twice, as I have here, summation from 1 to r of alpha I, there's an alpha I here, over mu I squared over this summation of 1 to r of alpha I over mu I quantity squared, all of that minus 1, because you notice this is the minus 1. Okay. Well, turns out there's a very nice Cauchy-Schwarz inequality. Which takes various forms, by the way. But in our case, it can be written as follows. For AI and B sub I, it writes as follows, that the summation of AI times BI, that whole thing squared, is less than or equal to the sum of the AI squares times the sum of the BI squares. Now, if we choose a particular value for the A's and the B's, I'm going to let AI equal the square root of alpha I. I'm going to let BI equal the square root of alpha I again, and this time divided by mu I. And let's use the Cauchy-Schwarz inequality for the equation above. So that Cauchy-Schwarz says that the summation of AI BI, which is AI over mu I, that quantity squared, is less than or equal to the summation of alpha I, that's AI squared, that thing times the summation of alpha I over mu I squared. And what is the summation of the alpha i's? In our case, it's equal to 1. Those alpha i's are adding up to 1. So this is equal to summation alpha I over mu I squared. Or I can rewrite that as saying that summation alpha I over mu I quantity squared over the sum itself squared, alpha I over mu I quantity squared, is greater than or equal to 1. And in fact, that's exactly what I had up here as the coefficient of variation. So it's greater than or equal to 1. In other words, if you want CB squared, which is twice the summation alpha I over mu I squared over the sum squared, minus 1 is greater than or equal to 1. Goes to the factor 2 up here. This thing itself is greater than or equal to, so this whole thing is greater than or equal to 1. So yes, I get a coefficient of variation which exceeds 1. Okay. So now that I've got that, let's use it. So now we could study, as we did before, let's start with, say, MHR1 or HRM1 or HRA slash HRB slash 1 by specifying what the stages do. Now, let's see how we might handle that. We're not going to go into too much detail. Let's use the following example. Let's take the two-stage case. Let's assume we had mu1, mu2, case we saw before. In fact, let me just copy that for myself. Let's look at what the state diagram will be, okay? Well, I've got a state 0, for sure. Nobody in the system. Now, from state 0, where can I go? Somebody comes in. That person is going to choose either stage 1 or stage 2. And they have different mu's, so I better have different states for them. So I'm going to create a state 1 sub 1, another state 1 sub 2. State 1, 1 means there's one customer in the system and he is in stage 1. 1, 2 means there's one customer in the system and he's in stage 2. So let's consider that. Now, how do I go from out of state 0? I can get an arrival. What's the arrival rate? Lambda. But how do I go from state 0 to state 1, 1 with an arrival? So the rate lambda times what? Times alpha 1. And similarly, from state 0 to state 1, 2 at a rate lambda sub alpha 2. Now let's see where I go from state 1, 1. One guy's in service is stage 1. If he finishes, where do I go? Now to state 0 at a rate mu1. Not mu, but mu1. And similarly, from state 2, 1, 2, I can go back at a rate mu2. But out of state 1, 1, I can have an arrival. If I get an arrival, where do I go? No, 2 sub 1. Good. Good try. Okay. There's a state 2 sub 1, which means that there are two people in the system, but the guy in service is still in state 1. So that corresponded to an arrival. There's no alpha here because the alpha was chosen for the guy in service. So that's at a rate lambda. And similarly, there's a state 2, 2, and I go from 1, 2 to 2, 2, again with an arrival. Okay, now let's look at some departures. From state 2, 1, I can have an arrival, fine, go up. But if there's a departure, what happens now? This guy was in this stage. He leaves. From state 2, there's certainly one guy in the queue. He can go to stage 1 or stage 2. There's 2 cases. But whatever it is, there's only one guy in the system. So where do I go? You're smiling because it's a little messy, okay? So what are the possibilities? I can have that guy leave, and the next guy can choose to go into stage 2, and there's one guy left. And with what rate does that happen? At a rate mu and probability alpha 2. Or he could have chosen, the new guy can go back to stage 1 as well. So I could have this move here, which is a rate mu 1 again with alpha 1, etc. So there's certainly some, I won't label all of these. I can leave state 2, and I can go up here. Whoops. I won't bother label them. And dot, 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 okay? Now you can use inspection to solve this. It's basically a 2-dimensional system. You can solve it, okay? In fact, you can easily generalize this to an arbitrary number of stages, like I had up here. R stages instead of just 2 stages. And you draw more complex, there'll be then R chains instead of just 2 chains. And for R stages, let's choose that. Instead of just 2, what are we going to get? We're going to get the B star of S is equal to, again, a sum, just like before, I equals 1 to capital R, alpha I times Ri mu I over S plus mu I. But in fact, what I'd like to do is more than just one stage of these guys. The picture I really want, and I haven't made it clear, I want to create the following kind of structure. And I'll sneak that in right here. This is the service facility. And I'll begin with this next time. Yeah. Yes. Let me draw this picture, and then I'll be done, okay? The service facility looks like this. When the customer comes in, they choose one of R possible stages. And when they choose a stage, they march through, and they finally leave. There's no crossing. Once you hop along that chain. But each one of these has a different mu I and a different number of stages. So this could have, say, R sub 1 stages. Sorry. This could have R sub R stages. And each of them has their own mu. So what I started to write here was, for that strange case, it's these things to the Ri. That's the most general case we have. And you can write it down and solve it. Your question, John.
So when there was no customers in the system,
Yes.
we can have one person in the service one.
Yes.
We move to I1.
Yes. Yes.
When
You mo-
Second one, right?
Yes.
When there is already one customer in I1, there should be two customers in the system.
That's what the number 2 means.
But we put sub
The sub 1 means the customer in service is still in this link. He didn't move. A new guy came in while he's being...
that new guy picked the service one.
No, he doesn't pick it till he starts to enter the system, the queuing, the service system. Then he decides. When he comes in, he's not assigned to a service stage. He randomly picks a service stage when he enters service. That's the model. That's a good question. It could have been assigned upon his arrival, and then it'd be a different picture. You're quite right. Yeah.
Could you collapse this to one dimension by like drawing your circle around 1, 1, and 1, 2? Which is kind of 1 and 2.
Yes, you can, but I'm not sure the balance equations will be good, because you're quite right that this is P sub 1. Okay, but I still have to, if I drew circles around these two guys, then I'd have basically a one-dimensional system. But I need to know the rate at which they're leaving, and I don't know that. I can't say that the rate out of this box dynamically is the average of mu1 and mu2. So I have to keep track of that. That's where it falls apart. That was a good try, though. Okay, now, so what I've done with this picture, which I drew poorly, is generalize series and parallel. A whole bunch of series and a parallel set of those, each one different. Different length, different rates. Okay. And you could solve that. You get a very complicated equation. And this is what the B star looks like. Now, we could do it a little more general. We need not have insisted that every one of these have the same service rate, mu1. We could have made each one of those different. Really a generality, okay? And if we did that, we can write the B star of S. It's always easy to do, okay? It's equal to the sum again over R parallel stages, I equals 1 to capital R, of a choice, alpha I, and then what's the time in each one? It's not simply a fixed number to the Ri. In fact, it's a product of mu i's. It's mu ij over S plus mu ij, and the product J equals 1 to R sub I. R sub I is the length of the ith chain. But you could write it down, and you can imagine how to solve it. The equations are going to get messy. Complicated set of linear difference equations. One last thing, I'm going to take a moment extra. I'm going to show you yet another thing you could try. Remember, all of this is beautiful because at every step you have exponential service times. So you've not given that up. There it is. You can see it right there. Let's try another structure. Here's another structure. Suppose I have a service rate mu1, and another one mu2 to mu I to mu sub little r, say. I'm trying to draw a service facility. So somebody comes in. The first thing they do is they're going to join this service rate. Let me draw circles around each one of these. We're getting creative now. Come in here. But before you come in, you're going to make a choice. You may actually choose to leave. In fact, I'm going to draw a circle around the service facility. Well, now it's a square box. Okay. You may choose to leave the service box immediately with some probability. Let's call it alpha 1. And this will be beta 1. Alpha 1 plus beta 1 is 1. With probability beta 1, when you come and you choose mu 1, probably alpha 1, you get the hell out of there with no service. Okay? Now, after you finish mu 1, you again make a similar decision. You toss another coin with probability alpha 2, you're going to get the heck out of there. Probability beta 2, you continue to a mu 2. And so the picture continues. Oops. And here you leave with probability beta I plus 1. Here was a beta I, etc. And finally, when you finish with the last stage, there's not much room here. Yes, these are alphas. Thank you. These should be alphas. Very good. Let me move this over. It's in my way. I'll move this guy over. When you finish that last stage, you can only leave. So this is with probability 1. This is the service facility. Sort of interesting. There's a name for it, by the way. It's called something developed by a fellow named Cox. Great mathematician, by the way. All over, we know that alpha I plus beta I is equal to 1. And I can write down B star of S by inspection. So can you. So let's do it. B star of S is the following. Probably alpha 1, I spend 0 time. And what's the Laplace transform of an impulse at 0? Number 1. 1 in transform domain is the unit impulse at the origin. If you don't believe me, check the table. Okay? Or we're going to go through a bunch of things. We're going to have a sum from I equals 1 up to R, the number of stages, of probabilities beta 1 times beta 2 times beta I times alpha I plus 1, which means you leave just before you enter the I plus 1 stage. And if you do that, you're going to have a product of service time densities. Let me move this over a little bit. And that sum goes from j equals 1 to I of our friend mu j over S plus mu j for all possible j's up to I. We could write that down by inspection. That's not hard. But now you got to write down the balance equations. You got to draw the state diagram. It's not too complicated, but again, it's a set of linear difference equations. All of these B stars that I wrote down are rational functions of S. Namely, ratios of polynomials to polynomials. That means their poles, the zeros of the denominator, must lie in the negative half plane. If this is the S plane, and this is the real part and the imaginary part, I'll call it j omega, that's the imaginary part. all the poles have to lie on the negative real line. But in fact, you can get generality by allowing some complex poles. It's not physically real, but you could write a B star down for that. Can get more generality by allowing complex poles. Conjugate pairs, by the way, complex pairs. So you could, in fact, get poles like that. And you can still write down the equations. By allowing that, you get complete generality. So we can cook up any B star we want. And distill for any rational B star of S. Now, we can do this for the interarrival time and do this for the service time and generate any GG1 system for rational service time and arrival time densities. And then you write down linear difference equations, use the inspection method, and you're stuck with a nasty set of linear difference equations, which in general you can't easily do. But they're linear. And what likes a large number of linear equations? What's your major? Yes, computers love to solve large numbers of linear. They hate nonlinear. They love linear. They go right for it. So you throw this on a computer and you've solved it, okay? And you can get an infinite set, in fact. Okay, in fact, if it gets to be an infinite set, then you can use an approximation. And also use an approximation to go from a non-rational to a rational. Except it's a pain in the neck. But what I'm saying is this will lead to an approach to solving GG1. It's a very hard thing to use, and typically we don't. So we're going to spend the rest of this quarter finding ways to handle these cases, the MG, the GM, and the GG, using more analytic techniques. But my point is that Erlang, bless his heart, showed us an approach to solving any of these queuing systems just by generalizing the exponential. And it's really a great accomplishment from a guy who was not a mathematician. He saw the power of the exponential. Okay, was there a question line here? I've run over 10 minutes. Apologize. Okay, see you not Monday. Monday's a holiday. That's what this class is making up.